target reliability levels. With this, we come to the last major topic of this course. So let's look back and see how far we have come and what we learned along the way. We started with part A, which was lectures 1 through 9, and we started with what this course expects to cover. Then we moved on to the basics of probability theory, the basics of random variables and distributions. We discussed quite a few discrete and continuous random variables that occur commonly in structural reliability theory. We talked about joint distributions, and we ended part A with Monte Carlo simulations, particularly the generation of discrete, continuous, and dependent random variates. Part B, which was lectures 10 through 18, we gave an overview of the history and how the subject of reliability came to be. We defined the basic terms. We spent a good amount of time in how to formulate reliability problems, and then discussed how systems can be represented in terms of its constituent elements and what different types of redundancy there are for a system. Then we spent a series of lectures on the time to failure, which we called the phenomenological approach to reliability, because that was the only random quantity, the TTF, in defining the performance of the item in question. So we discussed the reliability function, the hazard function, various metrics like mean time to failure, mean residual life, and so on. We also discussed estimation of TTF statistics from test data, and then how a system time to failure may be described in terms of the element times to failure. In part C, which was the longest part, lectures 19 through 30, we moved to physics-based description of reliability, of failure, and we started with a component formulation, component reliability from the capacity demand point of view. In that context, we learned the first order reliability method for computing failure probability, the second order reliability method, and then Monte Carlo simulation based techniques, including the variance reducing importance sampling approach. Then we brought in the time aspect, and we first looked at components that age or loads that change with time but in a non-random manner, and then we introduced first randomness in the loads as a pulse process with identical distributed load magnitudes, and then pulses that occur randomly in time according to a Poisson process, and then we allowed both the strength and the load to vary randomly in time, and under certain assumptions we looked at that first passage problem. We then looked at the time dependent reliability, how it's affected by repair and how decisions may be taken. So we looked both at perfect repair and imperfect repair. We ended part C with a system reliability discussion, and obviously physics-based capacity demand type. So we looked at first the series configuration, which was appropriate for non-redundant systems or multiple failure modes for one component, or dual or multiple performance levels for one component, or dual or multiple load combinations for the same structure. We then looked at parallel and other redundant configurations, in which we looked at two extreme cases or two ideal cases. One was the brittle failure of elements, and the other was the ductile failure of elements. And because of the load sharing nature, we also discussed the effect of failure sequences. So that was the end of part C, and what is going on now part D, and we have 6 lectures, and today is the lecture number 34. What we have already covered in the first 3 lectures of part D are reliability based design codes, their evolution, the philosophy behind them, the format of design equations that involve more than one factors of safety, the partial factors, and then we showed clearly how the partial safety factors, or even one safety factor, can be tied to a specified target reliability. And then we showed for a class of structures, which is very useful for design, how a set of partial factors can be optimized, and then worked through a few examples. What we are going to start today is target reliability levels, how to set them, and obviously a very important question is how safe is safe enough when we are talking about life safety type limit states. And then we will end this week with a few more concepts that have come up during our discussion, those of robustness and that of resilience. So that is the plan for this week. So let us start.